Okay? Okay. So let's start with today's seminar. Today's seminar is about OSIRIS. This is the first instrument on the GTC telescope. The principal investigator is Jordi Cepa, who is the speaker today. You may all know that OSIRIS started officially in 1998. So after a little bit more than 10 years, OSIRIS is now at the telescope, and it's very likely that next week observations will start at the telescope. So now, Jordi, thank you very much for giving this talk.
Vale, bueno, diré algo en castellano de entrada. Hola, buenos días a todos. La verdad es que estoy absolutamente impresionado por la gran cantidad de personas que han venido y me han pedido que dé la charla en inglés. Entonces, pues bueno, pues la voy a dar en inglés. Okay. I'm going to talk you about the first results obtained during the commissioning of OSIRIS instrument at the GTC, and essentially what I am going to talk you about in this talk is, first of all, I will show you the team that has been responsible for designing, building and testing the instrument. I will remind you a little bit about the main characteristics of the instrument. I will show you some pictures showing some of the moments when moving the instrument from here to La Palma. Probably you have already seen some of them. I mean, I will repeat again. I will show you some of the commissioning results obtained so far, and talk also about the pending task and the commissioning of the remaining modes. And finally, with the upgrades that are expected and some of them that are already underway. Well, this is the team. I put everybody here. Well, I hope that I did not forget anybody. In order to show you that this is a teamwork and it's a lot of people is involved and has been involved in this instrument since the very beginning. Of course, there are engineers and there are scientists as well. The scientific team has been more stable in the sense that we have been accreting people, not living. But in the engineering side, I show you here, these are the engineers involved right now. By the way, there are the people of the mechanical workshop as well that I forgot, just remember right now. And engineers from Mexico as well. All these engineers are essentially not all of them working 100%, but most of them, or a significant fraction of them, are part-time. And all these engineers are not working right now in the instrument, but they were sometime in the past. So I put everybody here. So and even that most of them are not working at the IAC. They left. So this is just to show you all the people that has been involved in time in the instrument, and to remember again that this is a teamwork, and all these people is the people that has to be thanked about the instrument. Okay, now some reminders is that OSIRIS is an instrument designed as a multi-purpose instrument, so it's not an instrument for a specific purpose, and has several observing modes: imaging in broadband and in narrowband using tunable filters, a long-slit spectroscopy, multiple spectroscopy, and fast modes, both in photometry and spectroscopy, using different techniques. I'm not going to enter into detail in any of the sub-modes that are listed here. Too many modes anyway, difficult to commission. So the basic characteristics of the instrument: the field of view with a small percentage of shadowing in the focal plane, plate scale, detectors, a mosaic of 2 detectors, 4K per 2K. The broadband filters are the slow and set, and you can use as well the order sorters for the tunable filters. The tunable filters need an order sorter that is about between 300 up to 500 angstrom full width of maximum. And then, of course, you have the tunable filters for narrowband observations. You can tune essentially your wavelength anyway from 365 nanometers up to almost 1 micron. And the tunable, you can also, for each wavelength, select between different possible full width of maximums available. The minimum ones, it's about 12 angstrom, and the larger ones about 20 angstrom. I put here this in red because this has been a change in what was specified before. And I will, this was produced by the different temperature at which the calibration was done and the temperature at which the instrument is at the NASMIP focus. Temperature, it's interesting to say that, has produced several specific problems that I will come back further on in the talk. These are the spectral resolutions that are available, and of course you use multivolume spectroscopy using masks that you design. Okay, now just a few words about tunable filters versus standard narrowband interference filters. Is that, of course, in the tunable filters you can tune the wavelength and the width and maximum. You cannot, of course, in the standard filters. Also, for these widths that are quite narrow, it's difficult to obtain standard filter with a reasonable efficiency, especially in the blue, while in the tunable filters you can get quite high transmissions. The spectral response is another difference that you have to take into account. The peak is Gaussian and has some wings, while a good standard filter is more or less square, depending on the layers that you deposit on the filter. Of course, one advantage is that doing a narrow band, you have to subtract the continuum, you need an off-band filter, and you can use the tunable filter for this purpose, and you get the same spectral response as near as you wish besides your own filter. While using a standard filter, you cannot do that. So this provides a very good continuum subtraction. There is a wavelength variations between center to edge. This is because we are in a collimated beam. And this is the same, either you use a tunable filter or a standard filter. It's the same. The only difference is that the wavelength variation is about a factor 2 smaller in a standard filter because the refraction index is higher. Okay. Also, that the tuning, you can change the tuning in about, say, some tens of milliseconds. Okay, so this is just a conceptual example that you are able to deblend H alpha from nitrogen 2 by using the tunable filters adequately tuned. Okay, now let me show some pictures about the travel from the instrument from here to La Palma. These pictures were obtained, some of them by Ivan, others were obtained by Jose Carlos. And it's here, so these are the people to blame or to congratulate about that. This is just the arrival to La Palma in boat. There are, several things happened during the transport. One of them is that we got a fine because we were driving these trucks very slowly through the highway going to the south. So it was an interesting situation. Another interesting situation is that we were in some auxiliary cars, after the truck, and we were stopped by the police just going out of the ship because we look very suspicious, probably. But, well, it's another interesting thing. Well, anyway, the instrument departs from here to La Palma, from the highway and the boat, and the instrument slept in the Palma harbor the first night. And the following day, we go up to the observatory. Maximum speed is about 30 kilometers per hour, so interesting. going there. This is just the arrival of the tracks. There were 2 tracks. This one is the one with the instrument that drove slowly, and this one is with auxiliary equipment going to the telescope. This is the unloading maneuver with the crane of the track. We get rid of the box, the wooden box. Of course, you have to get rid of also this plastic seal that was thermosealed in order to avoid damage of the instrument by dust and humidity and all these things. And after that, you can begin starting. The first day was just starting removing all the different mechanical pieces that were put in there in order to block the different mechanisms to avoid damages, and also to doing some functional tests in there. And after that, we push the instrument to the telescope. So we are in the basement, and we, of course, we put some air pads below the instrument. So the instrument was floating over an air cushion like a hovercraft, and we just push a little bit, and the instrument, we transport the instrument from the arrival place up to the lift. Of course, while doing that, some people were just enjoying the situation, because too many people pushing anyway. 2 or 3 people were enough, but everybody was here trying to, well, interesting. So this is the lift. So the instrument is pushed into the lift. I forgot to say, but this piece, yellow piece here, as we will see, is for handling the instrument and tilting it to get it installed. Okay, this is the lift. So the instrument has arrived to the dome, and of course we have to use the cranes of the dome to lift the instrument up to the Nasmyth platform that is here. Okay, this is just the arrival to the Nasmyth platform. And, okay, now there is one motor here that is used to tilt the instrument 90 degrees in order to face the Nasmyth interface. So, tilting a little bit and approaching the interface and screwing the bolts. And, okay, that's it. These are the people from the mechanical workshop and mechanical engineer in charge of mounting it. So they did it very well, and no need to remove it, hopefully, in the future. Okay, that's it. Now, resuming the talk, now I am going to talk about some of the results obtained during the commissioning. The commissioning is still ongoing, it's not finished, and but we have had quite bad weather conditions, so it was difficult to finish everything that was expected. Essentially, what I'm going to talk you a little bit is about the basic test, some about the shutter accuracy, calibration line maps, the calibration of the photometric system, and a little bit on the wavelength calibration for the tunable filters. So the basic tests are, of course, checking the optical alignment, doing some functional tests of the mechanisms. Some of the mechanisms gave some problems. I will talk you a little bit about that. Doing the integration, and the first test in imaging long slit and multiple object spectroscopy in dome and in the sky, looking for ghosts and some other features, unsuccessfully looking for ghosts and all these things. So, the instrument passed this test. The image quality, the instrument distortions, the mechanical flexures, everything was expected. So, fine at this moment. And let's go to some more specific tests that you were more interested to hear about. It's about the shutter accuracy, for example. Shutter is nearby the collimated beam, not exactly in the collimated beam, but nearby. It is in the middle of the camera lenses. And a very important feature is that everybody should ask for is which is the minimum exposure time that you can use obtaining good results. And good results means uniform flat fields and, accurate photometry for your favorite targets. So what we did is a series of sequences with different exposure times. And after debiasing and flat fielding, the image is just dividing, for example, the 1 second flat by the sum of smaller exposures, yielding the same final exposure time. Of course, we observe also standard stars in order to check the accuracy in photometry, but we have not yet obtained the results. So the statistics are that even for 50 milliseconds exposure time, you get a uniformity of about 1%. So this is very good. This implies that you can, if you wish, you can obtain images of 50 milliseconds exposure time, ensuring your photometry. This is an image of the result of dividing one image by the other. This was obtained by Alessandro. And you can see that it's quite flat. And if you take some profiles in the vertical direction, you find that, okay, there are some signatures of variation, but within 1% of the signatures. Okay. We also obtained quite a lot of line maps. We have to repeat several times because we had problems with exposure times and all these things. But anyway, Ana Perez did it very well, the work of labeling every line that you can identify. This is like, as we say in Spanish, es como buscar una aguja en un pajar. La diferencia es que está lleno de agujas. Pajar. Okay. Well, this is for the neon lamp, and this is for the mercury argon lamp, and you can see the different lines. Okay, so this is the things. These are the things that you can use for calibrating your spectra from the spectral line. It will be in the operating manual. We observe quite a lot M67 in order to characterize the astrometry of the mosaic. And we did several exposures moving the cluster around the field with the different slow-on filters and without filters as well. And the results these are the results that were obtained by Angel. And essentially here is this is one of the CCDs. This is the other CCD that conforms the mosaic. And I mean, there is a little trace in every position that is a factor 30 amplification of the distortion in pixels. So the distortion is quite small, as expected. This is the plate scale, measured plate scale, and this is the instrument position angle in order to get your images properly orientated according to the cardinal points on the sky. The aim is providing the FITS headers with all this information that you will need in order to, do the astrometry, the proper astrometry of your images. Okay. Fine. About the photometric calibration of the slow-on filters, we obtain images of several standard stars at different air masses, and this was obtained by Ana Perez and Emilio Alfaro in Granada. And this is just to the extinction derived and the error in order to show you that the NIC was reasonably good to do this work. And these are the photometric transformations. The 0 point is arbitrary, chosen 25. For one of the CCDs, these are the slow-on magnitudes, and these are the measured magnitudes. And these are the differences between one CCD and the other and the RMS. So, the photometric system is characterized. And we obtain some measures of the instrument efficiency, comparing obtaining images of the same standard stars through the instrument and through the acquisition camera of the telescope. We know quite well the transmission of the acquisition camera and the transmission of OSIRIS, of course, but this was not the one to be taken as reference, but we took as reference the acquisition camera, and we knew which was the transmission of the lenses and the CCD response and whatever, and with these filters and obtained these are the instrumental magnitudes that we obtained. So the OSIRIS is more efficient than the acquisition and guidance camera. And these are the predicted transmissions for OSIRIS. So this is consistent. This result is consistent with the result obtained experimentally. And this, of course, includes the optics and detector, not the telescope. So, okay, that's fine. We are fulfilling specifications. Transmission is as expected for the instrument. That was very good, as I told you in the previous talks. And when going to the 0 points, the measured 0 points, we find the difference between the measured 0 point and the calculator, the World Wide Web calculator 0 point. And, of course, the reason of this difference is that we have the mirrors of the telescope. So, I mean, the mirrors of the telescope need some reluminizing because some of them has some, I mean, of course, there have not been time to do that. It will be done in the next month. So, essentially, the message is that there are some differences that indicate that the mirrors need reluminizing, and you have to affect your integration times according to the calculator by a factor about 1.6 in order to compensate for that. This problem, of course, is a temporary problem that will be solved very soon. Okay, now going to the photometric calibration of the order sorted filters, we did the photometric calibration obtaining a slitless spectra of standard stars for each tunable filter. We did not finish because there are about 25 order sorters, so we need to finish the work with some of them. I'm only showing one of the results for one of the order sorters, and this is the transmission that is very good and fulfilling the specifications. We did that in different positions along the field in order to check for differences. Anyway, these filters has already been characterized in the laboratory, and all the measures are I mean, about to be put on the user manual. Okay, if we do the same with the slitless spectra of standards through the different grisms, we obtained for the case of the grisms R1000. This was obtained by Ana Perez again. These are the efficiencies for these grisms versus wavelength. This includes the telescope, so this has to be corrected by a factor 1.6, essentially in mid. Okay, so the efficiency is quite good. We obtained, just for fun, spectra of compact planetary nebula. Was not our intention to obtain this spectra. What was just that we were calibrating the tunable filter by a very wide slit put on a compact planetary nebula. So we said, okay, let's take a spectra in order to identify the lines, and that's it. So this is just, I mean, has no use, only for, I mean, confirming that everything is okay. So let's talk now about the wavelength calibration of the tunable filters that are the most tricky part of this procedure. Of course, the most tricky because it's not a standard. It's a standard calibrated spectroscopy and full band imaging and whatever, but not for the tunable filters. So just to remind you that the tunable filter is an etalon that works at a micron, few microns gap, and that you change the spacing using a piezoelectric working at high voltage, and you measure the distance between the plates, what we call the gap, the Z units in bit, so arbitrary units. So you need to establish a relation between the wavelength that you want to tune and the gap in bits. This is the key of wavelength calibrating the tunable filter. So we did some tests on the sky using planetary nebula, compact planetary nebula, and we found that was possible to do a wavelength calibration with an accuracy of about 1 to 2 angstrom. To use as wavelength calibration, wavelength calibrators, it's necessary to use a combination of lamp and planetary nebula, depending on the line that you want to observe. Of course, this is not finished. We need to check for more, to do more dome and sky calibrations. The reason is that we could not finish because we got some drifts on the Etalon gaps, probably attributed to electromagnetic interference, and we are going to solve it tomorrow, hopefully. So the stability against temperature, it's that you can work easily with temperature gradients up to 0.25 degrees per hour. That corresponds to the difference between the tunable filter and the telescope structure of about 2.5 degrees. That is quite high, with the, which implies the standard operation of the telescope. And we test the operation with a gradient of 0.6 degrees centigrade per hour successfully, but of course in this case you would need to calibrate often, about every half an hour or so, in order to check that there are no drifts. Anyway, we were not able to do more tests with higher gradients, because these higher gradients are not do not happen very often. So this is the reason why we. So the message that I want to transmit you is that the typical gradients are on this range, not on this range. Okay. Anyway, there is a tool for correct the temperature drifts of the tunable filter online. This has been successfully tested in the laboratory and will be implemented quite soon. And final word is that the humidity inside the instrument is very stable during several hours, even with an increment of humidity in the dome. So as a reminder, the instrument is closed and dry air is injected inside the instrument. So the instrument is humidity and temperature, well, humidity controlled, temperature is partially controlled. Okay, this is the laboratory calibration obtained for the tunable filters. So, as I told you before, you have here the gap in bits, and this is the wavelength. So this implies that if you want to select the wavelength of work, just go here, and each line represents the different full width half maximums that you can choose. So you need this wavelength, and you need a certain full width half maximum. So you have to go here, and you get the gap that you have to set in the talent. Of course, this is in laboratory. You need to calibrate that in order to check for the differences between laboratory and the day. Okay, because this can move slightly a little bit from day to day, and you need to recalibrate that in the telescope. It's quite straightforward. It would take about 2 or 3 minutes doing that. Okay, this is a set of calibration lamps for the different full width maximums and intensities and so that we are going to use. This is a catalog of compact planetary nebula that can be used for calibrating your favorite emission lines. And summarizing the commissioning results obtained so far, so the instrument is integrated in the GTC, the mechanisms are working, and we are working with the updated control release. Most of the imaging and spectroscopy tests are completed, and data reduction and analysis is underway. TF calibration is underway as well. We need to calibrate the tunable filter to check the calibration again. Instrument throughput is as expected, and the instrument is already doing science verification proposals since 1 week, as I was told. 1 week? Yes, more or less 1 week. Okay, which are the pending tasks? So we encountered some technical problems that, for example, it's interesting to say that even for a non-cryogenic instrument, or perhaps in spite of being non-cryogenic instrument, temperature affects the mechanisms. What we find is that the working temperature in the laboratory was about 20 degrees or so, and when going to the dome, the temperature was about between 5 and 10 degrees. And then it was necessary to give more torque to the motors in order to move the mechanisms. So we had to slightly reduce the speed in order to increase the torque, and everything was solved, but of course this took a while to realize about that. So this problem is solved. No, the mechanisms are working okay, no problem. We have a residual problem, that is we have some source of noise as the NASMIT platform that affects both the CCD readout noise and the initial tuning of the tunable filter. We hope to solve these problems between today and tomorrow, hopefully. There are, Enrique and Roberto are now at the observatory trying to solve that, and I will go to the observatory tomorrow in order to try to check if the problem with the tunable filters is already solved. Anyway, well, the red tunable filter is the one that we are using now. It requires more or less about 1 week, less than 1 week, but I put 1 week to be sure, for doing the wavelength calibration and the flux calibration of the tunable filter and having it completely operative. About the blue tunable filter, this takes a while because we have to finish the laboratory calibration. That takes few days. And from this data to define and purchase the order sorter filters. This takes long because the company has to fabricate, to manufacture these order sorter filters. This is the main, the longest delay of the reason of the longest delay. Of course, doing the wavelength of flux calibration, since we have already done that for the red tunable filter, this will be shorter for the blue one. And about the VPHs at resolution 2500, the problems with the manufacturer has been solved in one way or another and will be available in a few weeks. The more other commissioning tasks that are pending and that will be tackled this semester is implementing the flexures correction system by moving the collimator according to a lookup table depending on the rotator position, to test the tunable filter shuffle modes, multiple object spectroscopy, and the fast modes in photometry and spectroscopy. So, talking about upgrades, there are several upgrades expected. One of them is implementing an integral field unit consisting of, fibers going within the focal plane with micro lenses of 0.6 arcsecond in diameter, and we are thinking in about 2 integral field units, a compact array, relatively small, and a sparse array that is larger. Also, there are several proposals to design and fabricate the additional VPHs. There are funds coming from 2 projects right now. The VPH is expected out of resolution 5000 in the blue, working in second order, probably reaching or hopefully reaching H alpha as well. This is a resolution in this wavelength range that is not available in other 10-meter telescopes. And the design and the specifications of these filters these VPHs are about to start. And also using the Consolidator project, there are some funds for designing and fabricating additional VPHs working at 10,000 resolution in the red. Okay. And it is a higher resolution etalon that is about to be available soon, provided by Mexico. And it's only a matter of everyone purchase the preferred order sorters. So this is the things that I wanted you to talk about. And finally, just to show you some pretty pictures obtained using the instrument. This is GK per se, that is the nova remnant. It's obtained through an order sorter selecting H alpha emission line. We also obtained some images of the comet Lulin. That was very difficult because the proper motion was very high. In fact, you can see here, picture is, for example, this is a star, and of course, taking the different pictures in the different filters, the comet was moving with respect to the stars, and when doing the final RGB composite image, we centered the comet, and the stars were displaced. Okay, and finally, this is my preferred one. This is the typical one, of course. Perhaps you can think that it does not look very nice, but I can assure you that in the screen it looks very beautiful. You can see clearly the dust lanes. This is an RGB composite images as well, using both a mosaic of both detectors. with some dithering to remove the gap within detectors. And this image is about 3 minutes, obtained in 3-minute exposure. This is what I want to do. About 1 second. That's it.
Okay, so this is time for questions, comments.
If I have understand correctly, the flexor compensator doesn't work right now.
The flexor compensator is not enabled right now.
So
it's not the same.
What's the longest?
The longest exposure
for a spectra.
In fact, the flexor compensator, you need it if the rotator is moving quite fast. For example, if your object is very nearby the zenith, or but with exposures of 1,000 or 2,000 seconds, I don't think that you will notice any problem, unless, I mean, you are nearby the zenith.
Okay.
Two questions. What are the expectations for the
It's the 2,000. Okay. It's here, and the holder is being mounted right now. I mean, some pieces of the holder have not arrived yet at the IAC. But once they arrive, it will be mounted and shipped to La Palma. I would expect that less than that.
I have missed whether we have spectral lamps in the blue part of the spectrum. I have not seen the
Oh, there are the mercury one. You mean this? Oh, this is a saturated star. In fact, most of the point-like sources here are saturated. I say point-like sources because probably there are something that are not exactly galactic stars.
Can you tell us something about the detector characterization?
Yes, the cosmetic is very good. And the readout noise that we measured here, the readout noise at the IEV, is about in 100 kilohertz speed, is about 4 electrons. It's higher right now at the Nesmith platform, and this has to be solved. It's probably a problem is of interference, electromagnetic interference. It's about a factor 2 higher than expected. No, it's not included. This affects only if you are going below the sky, photon noise, that taking into account that you are working at low resolution, it's unlikely to be the situation. You can observe fringing about 900 nanometers above. I mean, we use, for example, you cannot see fringing in the I slow and filter. You can in the Z filter. 5%.
Yeah, a couple of questions. The first one is, what was the typical scene during the commissioning?
Typical. It ranged from 0.5 to 2 arcseconds.
Well, mean, let's say mean or mode.
Mean, well, typical thing is about 1 arcsecond or something like that. 0.9, 1.2, something like that. We measured during several hours, 6 hours, a sync of 0.6, even less than 0.6. Even in the bluest filter.
The second one is maybe it would be useful if you comment a bit about the options available next semester? We are applying for time now for what is available.
Except the blue tunnel filter, I would expect that everything is available.
Not the blue tunnel. The blue tunnel will not be available.
I don't think so. It's a matter of the delivery time of the order sorters. I mean, the tunnel filter is here and is being characterized, and this is the easiest part. Well, it's not the easiest part. It's the most complicated part. But it's more difficult to get the filters in place in time, because the manufacturing companies took quite a long time to design and to build the filters. This is the main problem.
And the last thing is, you mentioned that you did some tests of the Morse mold. Is the Morse cutting machine already available?
No, not yet.
Not yet.
We did the exercise was just observing M67 with multiple spectroscopy mask. Possibly Rasilla did that, and the mask was cut in the mechanical workshop here. And now they are selecting, in the team, we are selecting the mask, the cutting machine to cut the mask.
When will it be available? If you are selecting the machine now, will it be available at the beginning?
I don't know. I would expect that it would be available in summer or before summer. Anyway, you can cut the slits here.
I understood that even the fast photometry and spectroscopy modes are offered, even though they are not commissioned yet, right?
Mm-hmm. Yeah. We are working with shuffle, with charge shuffling usually, because for calibrating the tunnel filters, you need to use charge shuffle. So we are working with charge shuffling. So it's working.
More questions, comments? Jordi, do you plan to put this information on a website of the instrument, or GTC is going to do this? Or?
Well, no, we are planning to, this is part of the information that will go into the user manual. Might be available on the web. I didn't realize of that. But of course, this information is more precisely, put on the user manual, and the people can just have a proper, information and complete information in the user manual.
And the user manual is going to be ready before the cut deadline, or?
It's unlikely. It's about 3 weeks from now. No, less than 3 weeks. It's difficult.
More questions? So let's thank Jordi again for his